Officially recording. Class has officially started. Hello, everyone. It's Wednesday. It's great. Course logistics things. Uh, I don't know that I have much that I haven't already said. Um, Taking a look at grade scope. There's the late due date for problem set 4 is tonight. So if you haven't already done that, please make sure to do that. Problem set 5 is out. PA2 is happening. I just like a few minutes ago released program assignment 3 onto Brightspace. So there will hopefully be a Gradescope autograder for that by the end of today or maybe tomorrow. But you'll have 2 weeks from today to finish that. So it'll be due by midnight Wednesday, July 1st. And yeah, so take a look at that. That is going to be about graph stuff, broadly construed. So more specifically about like shortest path algorithms, which we're going to talk about hopefully today or tomorrow. Um, so yeah, program assignment out, uh, problem set to take a look at. The exam is looking at this, it's about halfway graded at this point. Hopefully we'll be able to release all of the exam scores before the end of this week. That's all I have on the administrative side of things. Are there any questions before we get started with content? All right, if there's no questions, let's get started. Whiteboard. All right. So last time, yesterday, we talked about graphs. We did a lot of definitions, and we talked about sort of graph representations, right? So if you remember, we had the adjacency list, where the idea is each vertex stores a linked list of vertices of, maybe I want to say just adjacent vertices. We talked about the adjacency matrix. Each pair of vertices indicates whether it's connected by an edge. And then we had the incidence matrix, where for each edge vertex pair, we record whether, I can do better, whether the edge is incident. Yes, people remember this. We talked about the three sort of data structure representations of graphs and maybe some pros and cons of at least the first two, with the understanding that you are probably not going to see very many algorithms that use the incidence matrix, at least in this course. There are other, the incidence matrix is great for doing like linear algebra with graphs, but that's we're not doing that. Okay, so I figured we could start by talking about some graph algorithms today. Well, actually, I guess before I do that, were there any lingering questions about any of the representation stuff that we talked about yesterday before moving on? All right. Seeing none. Let's do graph algorithms. Okay, so we want to start by talking about BFS and DFS, right? So these are like breadth first search and depth first search, right? Maybe it's worth just writing this out for the notes. Breadth first search and depth first search. All right. We talked about these in the context of trees, right? Like as sort of the order in which you might traverse the nodes of a tree. But it turns out that we can think of this as, or we can think of these as operating on graphs as well, right? So the idea, I mean, the idea is very similar, right? So if we start with maybe DFS, and here I'm just going to copy sort of the the pseudocode from the book. But if we do some graph G, given some source vertex S, right? So the idea is given a graph, right? Maybe this is my graph. And maybe one is my source vertex, right? So I start here. Oh, this is maybe a bad example. Let's make this bigger. There we go. Yeah. So I start at one. I visit one. And then my neighbors that I can continue to visit are 2 and 5, right? I pick one of these to visit first. So let's say I visit 2. My neighbors are now 3 and 4. I then pick the other neighbor that I didn't visit. So I visit 5, right? So the order I've done these is 1, then 2, then 5. The neighbors here are just 4. Now I go back to 2's neighbors. So I visit 3 and then 4. And then I go back to five's neighbors. I notice that I've already visited four, so I don't visit it again, right? So I sort of visit uh, the vertices of the graph in this order. In particular, uh, the order or um, the iteration order is sorted by distance from the source, right? So uh, 1 is obviously a distance of 0 from the source. 2 and 5 are both a distance of 1 because there's a single edge. 3 and 4 are both a distance of 2 because I can take 2 steps to get to 3. I can take 2 steps to get to 4 in many possible ways. Of course, I could also take 3 steps to get to 4, but I don't worry about that. Okay, so if we write pseudocode for this, this is going to look very similar to our tree pseudocode. Um, but in particular, we kind of want to think of this as building a tree, right? So breadth first search kind of builds, if I just look at the edges that I've visited in my iteration, what I end up with is a tree where the source node or the source vertex that I started my search at is the root. And every vertex of my original graph is contained inside this tree. But not every edge is contained inside the tree. So in particular, it's a tree, right? The word for this is spanning tree. This is a subgraph on all vertices which is also a tree, right? So there's many possible spanning trees, right? I could have started at 5, in which case this edge, or I could have done 5 before 2, in which case this edge would look like that. That's still a tree. I could have I also didn't have to do this in like breadth first order, right? There's any number of ways that I could build a tree out of this, um, and later we'll talk about like uh, algorithms for finding the minimum spanning tree or the MST. Um, but for now, I just want to think about building this tree. So in particular, I also need to keep track of like the predecessor of each node, right? So I need to know that I visited 4, or I visited 4 as a child of 2. I visited 2 and 5 as children of 1. I visited 3 as a child of 2, right? So let's see how we do that. Um, we start by we have let's see, um, an empty, we can say maybe a table of distances, right? A table of predecessors. And then we can keep track of what nodes have been uh, visited as a set. Uh, visited, maybe I'll call this like to visit. So we have like a set of neighbors available. And then unvisited, all the rest of them. The pseudocode works by sort of assigning like colors to nodes, and maybe that's better, but I think that's harder for me to think about. So we can start by saying that the distance to the source is obviously 0, right? And the predecessor in our tree is null. It's the root of the tree, so we don't have a predecessor. And then we initialize a queue, and we enqueue our source node. And then just like we did with a breadth first search over a tree, we say while the queue is not empty, I dequeue a node. And then I can say for each the adjacent to u enqueue v, right? And then if v is not visited, to visit dot add v. And then we can say that the distance to v is 1 plus the distance to u, right? And then we can say the predecessor of v is u. Oh, and then I want to only enqueue if it hasn't already been visited. Maybe I actually want to say if v in unvisited. There we go. And then at the end of this for loop, I can say visited.add u. Right. It sure would be nice if I could. All right, whatever. That's fine. Maybe I'll zoom out a little bit so you can see all of this. But okay, yeah. So here's our pseudocode. If we track this iteration on this graph that I drew, maybe I can keep maybe I can draw like the tables of distances and the predecessors, right? So we start with 1 at a distance of 0 from 1, which makes sense. The predecessor of 1 is null, right? Okay, so we enqueue 1 into the queue. So maybe I'll look at the queue here. This just contains 1. I dequeue it, and then I look at all of the things adjacent to 1. So I look at 2 and 5. So I start by looking at 2. I haven't visited 2 yet, so I mark 2 as something that I need to visit. I mark the distance to 2 as being 1 more than the distance to 1, so that's 0 plus 1. which is 1. I mark the predecessor of 2 as 1, and then I insert 2 into the queue, right? And then for 5, same thing. I mark its distance as 1 more than 0. So the distance to 5 is 1. The predecessor of 5 is 1, and I enqueue it. Now I look at 2. I haven't visited yet, so I can visit it now. The distance is 1, or sorry, I look at every one of its every vertex that's adjacent to it. So that's 3 and 4. So maybe I start by looking at 3. I mark the distance. I mark the predecessor, and I enqueue it. I look at 4. I mark the distance. I mark the predecessor, and I enqueue it. Now I'm done, so I dequeue 5. I look at all of 5's children, or I look at all of the nodes adjacent to, or all of the vertices adjacent to 5. I see 4. But 4 has already been marked as visited from here, so I don't process it. It skips this if statement. So in particular, there's nothing else to do. So I'm done with 5. I look at 3. I dequeue 3. I look at all of its adjacent things. I see 4. Again, 4 has already been processed, so I don't do anything with it. And that's all of it. I dequeue 4. There's nothing adjacent to it. So I'm done, right? And so now I have this table of distances and this table of predecessors. So I can build the tree just by sort of looking at each vertex. And connecting it to its predecessor, right? So the predecessor of 2 is 1, the predecessor of 5 is 1, the predecessor of 4 is 2, and the predecessor of 3 is 2, right? So I can build this tree this way. And I'm also sort of guaranteed that all of these distances are the shortest, right? Why is this necessarily the shortest? Because there is another path from 1 to 4, right? I can go 1 to 2, 2 to 3, 3 to 4. But I know that that's not the one that I'm going to look at, or I know that like the distance to 4, I'm not gonna record that as 3. I'm going to record it as 2, because I know that I'm going to visit this path before I visit this longer path. Does it make sense? In particular, the fact that the iteration order is sorted by distance from the source kind of means that the distance that I record in this table for every vertex is necessarily the minimum distance, right? And in particular, this also kind of secretly gives me whatever the shortest path is, because let's say I want to know like a path from 1 to 4, right? So first of all, I can look at this table and I can read off that the length of this path is 2. Right? And then to actually figure out that path, I can say, okay, I start at 4. The step that I had to take before getting to 4 was looking at 2. So I can look up 2 in the table. The step I had to take before that was getting to 1. I can look up 1 in the table and I can say, okay, 1 was the source, right? So I can sort of read off this path backwards: 4, then 2, then 1. And so secretly, BFS is giving me a shortest path in an unweighted graph. Does this make sense? Do people follow the the sort of pseudocode here? and what we did with tracking like the distances and the predecessors. Any questions before moving on? All right. So that's good for breadth first search. I figure we can talk about depth first search. Oh, I guess before I do that, I should say BFS gives us the shortest path in an unweighted graph. In particular, it gives us the shortest path to any node from a fixed source node, right? Um, maybe it's interesting to think about the time complexity here, right? Um, just so we can compare it eventually to other shortest path algorithms that we find. So first of all, uh, look at the space complexity, right? What is the space complexity of of um, of our breadth first search algorithm? What's the auxiliary space I'm using? The main thing is I have to keep track of whether I have to keep track of like these three sets of vertices, right? Um, and then I have to keep track of a distance and a predecessor for each vertex, right? And by the time BFS is done, um, the the number of elements in both of these tables, or there's going to be an element in both of these tables for each vertex, right? So the auxiliary space is just proportional to the number of vertices. Where do we go? Here we go. The auxiliary space is just proportional to the number of vertices. If I look at the time complexity, uh, anyone want to share thoughts on the time complexity? Maybe I can pull up the pseudocode so you can take a look at that. How many steps does this take? If I have a graph with V vertices and E edges, how many steps does this take? How many times does this while loop run? You can shout it out in the chat. Is it also O of V? Um, that's a good starting point, right? I definitely have to do something for each vertex. But so this loop, this outer while loop runs O of V times, yeah. Um, but what about the stuff inside? How many times does this like for loop run? It runs for each edge. Yeah. So I end up with something that looks like that, right? Um, Later on, when we talk about other shortest path algorithms, they're going to look a lot like this. Just with some optimizations built on top, right? So, for example, we're gonna like instead of inserting things into a queue, we're gonna be more clever about the order in which we visit vertices to make sure that we still find all the shortest paths, but we kind of um, prioritize getting to the place that we want to faster. Um, and we'll talk more about that. But here we go. All right. So depth first traversal or depth first search. Let me see if I can find a better example from the book for this. Okay, here we go. Okay, so the idea of depth first search. So in a breadth first search, we started at a particular place and then we visited all of the vertices in order of how close they were to the source, right? In a depth first search, instead of doing things in a nice order like that, we're going to sort of try to go as deep as we possibly can, right? Depth first, and then we're going to backtrack when we find that we can't go any further, right? Um, so instead of just uh, of course, we're going to have a predecessor, right? Um, right, so we can still track the predecessor of each vertex. But we're also going to have this idea of like entry and exit time, right? So this is going to be when I like the entry time is when I first visit a particular vertex. The exit time is when I backtrack past that vertex, right? So we're going to track sort of both of these. Um, Let me write some pseudocode. This uses a let's start with the sort of helper function visit. At some particular vertex B. Oh, book calls it U. Don't want to get confused. Um, Maybe I should do this in the other order. Okay. We start by setting the predecessor of every vertex null, and um, every vertex is unvisited, right? we start the time, right? Because we care about the entry and exit time. Also for this, I could do this. Right? How do I get rid of this? There we go. Because we care about time and because entry and exit both start with an E, we're going to call this one discover and this one uh, finish, right? So entry is when it first discovers a particular vertex, exit is when it's finished dealing with that vertex. So this way I can abbreviate these with D and F. So start t equals 0. Um, and I can say for each V in V, oh, maybe I want to refer to this as just the set of vertices. If V is unvisited, visit V. And now we can talk about what it means to visit a vertex, right? So I start by noting that I'm taking a step, so I increment time, right? T plus equals 1. And then because I'm visiting this vertex, because I'm guaranteed that I'm only visiting a vertex that I haven't seen yet, this must be the time that I've discovered it, right? So the discovery of U is now the vertex that I'm visiting, equals T, right? I can set, instead of being unvisited, I want to be a bit more suggestive about how this works, right? I can say set every vertex to unvisited. Okay, so we say that we mark the current vertex as like currently being processed, right? So we're not done with it yet because it still might have a bunch of children before we backtrack all the way back to U. Um, so we mark it as visiting, and we say for each um, V that U has an edge to, if V is unvisited, the predecessor of V is U, right? This makes sense. The way we're visiting V is via the edge from U. So we set the predecessor, and then we visit V recursively, right? And finally, once we're done, I can say set U to finished. And because we're finished, we can increment the time and set the finish time of U to be the current time. This is a lot, so it's probably helpful to do this to sort of do this example, right? So maybe we can start. We set the predecessor of everything. Let me keep track of the predecessor here, the discovery time, the finish time, and maybe I also want to keep track of like the call stack. right? Because we have recursion, but I want to have like an explicit call stack so that I don't forget what's going on. Okay, so we start by setting the predecessor of 1, 2, 3, 4, 5, 6. I do this badly. I'm gonna move this up. Okay, so we've got predecessor, we've got discovery time, we've got finish time. And then I'm gonna keep this call stack over here. And then 1, 2, 3, 4, 5, 6. So here's my table. I start by setting the predecessor of everyone to null. Right? Then I start by visiting these one at a time. So maybe I'll start by visiting visit 1. Um, what does that mean? So I mark 1 as sort of in progress, right? And then I look at everything that is adjacent to it. And so in particular, that's 2 and 4, right? So I'll start by uh, um, oh, I visit 1, which means the time. Oh God, I need to keep track of the time as well. Uh, Time was 0. Now that we've visited 1, time is 1. So we set the discovery time here to 1, right? And then we visit all of its adjacent vertices. So in particular, maybe we start by visiting 2, right? Um, all right, we're visiting 2, which means time is now 2. So I set the discovery time to 2. And then I set 2 as being in progress. So I'm going to circle it in yellow. And then I look at all of its adjacent vertices. So I see 5. So I'm going to visit 5. Right. Okay, so I'm visiting 5 now, which means I mark 5 as being in progress. I increment the time and I set the discovery time of 5 to be 3. And then I look at all of its adjacent vertices. In particular, I see a 4. So I'm going to visit 4, right? Visiting 4 means I mark it as being in progress. I increment the time. Oop, forgot to switch colors. I increment the time. So the time is now 4. And I mark the discovery time for that. Now I look at all of its neighbors. I see 2, but 2 is not unvisited because it's been circled in yellow. So I don't do anything there. I'm done with 4, so I can pop it off the stack, right? So I go back to 5. 5 doesn't have any more outgoing edges. Oh, sorry. I'm done with 4. So before I pop it off the stack, I set it. I replace its yellow circle with maybe a green circle for finished, and I set the finish time, right? So the finish time of 4 is time step 5. Then I can pop it off the stack. I can visit 5. I see that it has no more outgoing edges, so I'm done with it, which means I again mark it as finished. So I'll put a green circle, increment the time, set the finish time to 6, and then pop it off the stack. Now I look at 2. There's no more outgoing edges, so I get no more outgoing edges, so I'm done dealing with it. So I circle it in green to mark it as finished. I increment the time, and I set the time, the finish time. Pop it off the stack. I look at 1. It has one more outgoing edge to 4, but 4 is not unvisited. So I skip it because I've already dealt with 4. And so I'm done with 1. So I pop it off the stack, or I increment the time. I write the finish time, and then I pop it off the stack. Oh, and I, of course, set it to green. That was the first iteration of that outer for loop. I started at 1, I visited 2, 4, and 5, right? Now I look at the second iteration. I look at 2. 2's already been visited, or yeah, 2's already been visited, so I don't need to do anything for it. I look at 3. 3 hasn't been visited yet, so let me add that to the call stack. Right. First thing I do when I visit, I mark it as in progress. I increment the time, and I set the discovery time for 3. The discovery time here is 9, right? Then I look at every outgoing edge that it has. It has an edge to 5, but 5 is not unvisited because it's been circled, so I don't do anything for that. It also has an edge. It has an edge to 5. It also has an edge to 6. 6 is properly unvisited, so I can push visit 6 onto the call stack. So now I call visit 6, which means I mark 6 as being in progress, increment the time, record the visit time as, yep, 10. And then it has no outgoing edges, so there's nothing to do in that for loop. So I'm done, which means I increment the time again. Or sorry, I mark it as finished. I increment the time, record the finish time as 11. And then I pop it off the stack, which puts me back at 3. There's no more outgoing edges, so I can mark 3 as being finished. Increment the time there, and mark the finish time for that, and pop it off the stack. Now I visited 3. Of course, the for loop continues. It looks at 4. 4's already been visited, nothing to do. It looks at 5. 5's already been visited, nothing to do. It looks at 6. 6's already been visited, nothing to do. So we're done, right? Oh, and I fully just forgot to record the predecessors. Rip. But we can do that, right? We can totally do that. So 1, the predecessor is null. 2, the predecessor was 1. 3, the predecessor was null. 4, the predecessor was 5. 5, the predecessor was 2. 6, the predecessor was 3, right? And so if we draw the graph based on this traversal, we see that we've included this edge, right? The 1 to 2. We've included the 2 to 5. We've included the 5 to 4. And we've included the 3 to 6. But the sort of tree, instead of getting a proper tree, right? If I look at the subgraph induced on these edges, it's now disconnected, right? I get the sort of forest. It's not possible to get a proper spanning tree from this graph because in particular, there is no there's no vertex from which like 1 and 3 are mutually unreachable, right? Like I can't reach, there's no path from 1 to 3, and there's also no path from 3 to 1, right? So any sort of source that I pick is only going to get me a tree that contains all of the vertices that are reachable from that. So yeah, there's no proper spanning tree here. A breadth first search in particular, if I were to start at 1 and do a breadth first search, I would get a tree that looks like 1, 2, 4, and then maybe I would look at 5 here. But then I would sort of stop, right? Like I would never even get to vertices 3 and 6 because there's no way to reach them from 1. Or I could start at 3, in which case I'd get like 3, 6, 5, 4, and 2. But I'd never hit 1 because there's no way to reach 1 from 3. Right. So the nice thing about depth first search, um, because the thing that we care about when we're doing a breadth first search is what can I reach from the source node and what's the shortest way to get there, right? So it doesn't make sense to sort of do a bunch of stuff for one source node and then pick another source, right? I could I could like loop over every vertex in the graph and sort of do this. Um, but for example, 5, right? 5 is reachable from both 1 and 3, right? So if I did a breadth first search starting at 1, I reached 5. I set the distance of 5 to 2, and then I started at 3, right? I look at 2, two's already been visited, whatever. I move on. I look at 3. Now I can visit 5. I either I either visit it, in which case I overwrite the distance, and now I don't know whether the distance of 1 that I've reported is the distance to I don't know which source node it's the distance to, or I don't visit 5 because I record 5 as already having been visited by 1, in which case I don't know the distance from 3 to 5, right? So it sort of doesn't tell me anything interesting. Like this edge kind of ends up not mattering, right? So I may as well like split this into 2 disconnected subgraphs and then perform a breadth first search on each of them if that's what I care about. Yeah, the idea is normally with something like BFS or with some algorithm based on BFS, we want to find the distance of every vertex from a particular source. And so it doesn't make sense to like run it on half the graph and then start over with a new source. Does that make sense? Cool. Um, uh, depth first search. So BFS is good for like finding short paths. Depth first search gives us a nice classification of edges, which I'm going to talk about. Um, this classification becomes important in some other algorithms. Um, so it's good to know which edge is what, or it's good to know what sort of edge each edge is, I guess. Um, maybe in the last few minutes, I'll talk about classifying edges. Um, something to note. Oh, by the way, no attendance poll today. Um, classification is not unique, right? So maybe there may be other ways to you might be able to classify an edge in a different way, right? You might be able to classify an edge as something else. This is not a unique way of classifying them. But the types of edges that we're going to think about are tree edges, forward edges, So a tree edge, a forward edge, a back edge, and a cross edge. The idea here is this is part of a tree edge is part of the tree that we build, or part of a tree, right? So if you remember, like DFS builds a forest of trees, right? So a tree edge is one of the edges in that forest. A forward edge connects, or maybe it's like a we all say like a composition of tree edges. A back edge is an edge that goes backwards, and a cross edge goes between trees, right? So more formally, if I look at an edge from U to V, right? Uh, if the predecessor of V equals U, then it's a tree edge, right? Otherwise, if V was visited after U, um, actually, how do I want to describe this? Oh yeah, okay. Uh, um, if I guess if there's like a sequence uh, of um, if V is in if V is reachable from U, and V was discovered after U, right? Then it's a forward edge. Else, if um, well, it's always going to be reachable, right? If V is in maybe the thing I want to say is if U is an ancestor of V in the tree, it's a forward edge. Else, if V is an ancestor of U in the tree, it's a back edge. Otherwise, it's a cross edge, right? So real quick, we can try to classify the edges that we have here, right? So maybe it's worth redrawing. 1, 2, 5, 4. Oh, there wasn't. Here we go. Okay. 3, 6. Right. So if I look at my traversal, I see that 1 to 2 is a tree edge, which I'm going to color in green because tree. But 1 to 2, 2 to 5, 5 to 4, and 3 to 6 are all tree edges because I visited these in my traversal, right? Um, I'm going to use purple for forward edges. So 1 to 4 is a forward edge. right? Because 4 is a descendant of 1 in the tree, but it's not an immediate descendant because it's not a tree edge. I'll use red for back edges. So 4 to 2 is a back edge because 2 comes before 4 in the tree. And then finally, I'll use maybe orange for cross edges. So 3 to 5 is a cross edge because it's none of the other ones. In particular, they're in different trees, right? So tree edge, um, back edge, forward edge, and then cross edge. All right, that's all I have. I will stick around if there's any questions. Otherwise, you are free to go. There's no uh, there's no attendance poll. So, and I'll pause.